In the previous lecture, I have introduced to you some general knowledge on control engineering, which also from the previous subject, 3133. And basically, our aim here is to design a controller. For the course, control system design, the aim is to design a controller. This is an example of a controller. Okay? So this is a plant or a system, and our aim is to design a controller here. And there are many controllers that can be used to obtain desired specification. For example, gain adjustment, the one that I put in red color, gain adjustment, PID controller, lead lag, state feedback, and all other controllers can be used to obtain desired specification. The one that I put in red color, I highlighted in red color is the one that will be in 3143. We will look into gain adjustment, we will look into PID controller, and also lead lag in time domain and in frequency domain. The one here, this is an example of a PID controller. KP, later we have KI and KD. They are the gain of PID controller. This is just an example. And again, the aim of this course is to give understanding and experience in designing PID controllers, which is in time domain, and lag compensators in frequency domain. So the course is divided into time domain, PID controller, and frequency domain, lead and lag compensator. I would like to continue with some revision on time domain, which is in chapter 5, chapter 4 or chapter 5, chapter 5 of 3133, which mainly discuss time domain. There are a few important terms which you should understand in order to proceed with control system design. You need to know transfer function, pole and zeros. You need to know first order system and their specifications, second order system and also specifications, under them response, effect of additional pole, steady state error, in particular final value theorem, which is the theorem used to calculate steady state error. You should know stability and also Rolls-Royce criteria, one of the technique to analyze stability of a system. Let's go in brief of those important terms. First is transfer function. Transfer function, we normally write GS. The transfer function is a ratio of output over input, C over R. C is here, R is here, C output, R is input. So transfer function is C over R in Laplace domain. Must be in Laplace domain with zero initial condition. And we normally show in a block diagram like this. RS, CS. And therefore, CS is GS multiplied with RS. That is transfer function. And roots are pole. Pole is the root of the denominator. We have transfer function, we have numerator over denominator. Here, this one numerator. The bottom one is denominator. Pole is the roots of denominator. So roots of the bottom one is poles. In contrast, zeros. Zero are the roots of the numerator. And pole and zero can be met on S-plane. We have S-plane. S-plane, we have alpha, sigma, which is real axis. And we have omega, j omega, in imaginary axis. So we can plot. We can plot the pole on the S-plane. For example, like this, like this. These are pole. Pole is shown by a small circle. Sorry, small cross. That is pole. Zero can also be plotted on the S-plane by a small circle. Zero like this. Zero. This one pole. One question, what is the importance of poles? Can someone explain what is the most important thing of regarding poles? Any input from the student? What is the importance of poles?
To identify the stability of the system.
Pole used to identify the stability of the system. Okay, good, Connie. Another thing, what is the importance of poles? Pole can be used to, pole determine the behavior of the system besides stability. Pole can show under dam, over dam, critically dam, and so on. Pole can be used to calculate rise time, settling time, overshoot, damping ratio, all related to the location of the poles. Therefore, poles are very, very important in control system. Pole basically determine stability and determine the behavior of the system. All the specifications that we discussed earlier can be determined by locating the position of the pole on S-plane. So make sure you are able to calculate or find the location of the pole in order to determine the behavior of the system. Next, first order system. First order first refer to the system order refer to the order of the denominator. Okay, we will see the denominator. The highest order is the system order. If 1, let's say s to the power of 1, that means first order. This is the pole. Is at A. Then the step response is always 1 minus e to the power of negative 80. And this negative come because negative pole. I'm sure it was mentioned, it was discussed in 3133. Therefore, we will have a response like this. All first order system which is stable with negative pole will have time response similar to this. Okay? It goes to 1 because when t approach infinity, e to power of minus at equal to 0. That's why finally equal to 1. Okay? And it's 0 because we know e to power of at will be like this, will converge to 0. Okay? So that's why when we have pole on the right, system will be unstable because e to power of at increasing, not converge to 0. So when you know first order system, pole on the right, pole on the left, sorry, system is stable. So this is the time response. All first order system. And time response in here will determine the performance of the system. And normally we calculate these three things. Time constant, remember tau, time constant, rise time, TR, settling time, TS, with their formulas. So you have to know the formulas and you have to know the definition. For example, time constant is 63% of the final value. Settling time is minus 2% of the final value. That is first order system. Second order system, more complicated because we have two variables. In here, we have zeta and omega n. And we have damping ratio, we have natural frequency. Both determine the behavior of the system. By having alpha, zeta and omega n, we know the location of the pole. Okay? Zeta and omega n determine the response, and we can see this one. This is actually for a second order system. Here zeta, and zeta, from zeta we can know the location of the pole. You see, as I mentioned, pole are very important. The location are important. Besides stability, it also determine the behavior of the system. This is zeta 0 called under damped. Zeta between 0 and 1, zeta 0 is for undamped. It's like a sine wave or cosine wave. Zeta between 0 and 1 is under damped. We have overshoot, then a small oscillation, then settle down. Pole are complex poles. Here, pole on the imaginary. We have zeta equal to 1 called critically damped system. No overshoot. It's like first order system. And two pole on the at the same place. Two pole on the same location on the real axis. Okay. And finally, we have zeta more than 1. We call over them. The pole are on the real axis, but they are not at the same location. They are at different location. The response is also quite similar to first order system. These are summarized in these responses. Undammed here. Here is undammed, underdamped, critically damped, and overdamped. So second order system. And in particular, in 3133, we give a special focus on underdamped response. For the case where zeta between 0 and 1. For an underdamped response, we will get a response like this. Okay, is going up, oscillate, and then stop. If this is a motor, for example, let's say I want the motor to rotate at 1000 RPM from 0, from idle, from not moving, idle case. So if the system is an underdamped response, so the motor will start to rotate from 0, will start moving, perhaps at this point 100 RPM, 200, 300, 1000, but because the motor is an underdamped system, it exceeds 1000, perhaps go to 1100 RPM. But it going down below 1000, oscillate, and then it stop. Not stop, it maintain at 1000. Okay. So this is quite a good system, but it takes time to reach the desired response, which is 1000 RPM. Okay. And the motor you can see is like oscillatory, a little bit. Okay. So all this determine the behavior or the performance of the system. System performance. How can we know whether the motor is good or bad? Then come all these time response specification. Rise time, peak time, overshoot, settling time, mentioned here. Okay, here show all the specification. EP we know pi over omega d. Ts is 4 over zeta omega n. Overshoot is equal to epsilon exponent formula for overshoot. There is a formula also for TR. All those formula you have to remember, because in control design we design based on the time response specifications. For example, the question will say design a PID controller so that the overshoot is 5%, settling time 2 seconds. So we need to find important parameters from the given specification. And of course, the formula need to be utilized. That's why you need to understand and you need to remember the formula. That is underdamped response. We also need to know what happens if we add poles. The formula all the formula, TS, TP, for example, I just take one example. Let's say TS 4 over zeta omega n. This formula applicable only to a purely second order system. All the formula, overshoot, TR, TS, TP, all only applicable to a second order, a purely second order system. Pure second order system meaning that no zero. Okay? And of course, second order, 2 poles. Only this. 2 poles, no zero. If we have 1, 0, 2 poles, then that formula is not valid, cannot be used. However, under certain conditions, a system can be approximated as a second order system. Sometimes, in some cases, we can approximate that higher order system into a second order system. If we can approximate, then the formula can be used. When if we can approximate that system similar to second order system, then we can use the formula. So when can we approximate higher order system into a second order system? Let's say I have 2 poles here at 2 minus 2, another pole here. So this is a third order system. This system can be approximated if the third pole is 5 times farther to the left, 5 times from the poles. If at least minus 10. From here to here, 5 times. If this is the case, then we can approximate the system as a second order system. And in that case, these 2 poles are known as dominant poles. They are dominant. The other one not dominant. That's why we can approximate as a second order system. But if let's say the third pole is here, minus 6, then we cannot approximate. Now the system is a third order system. All poles are important, all are dominant, then is a third order system. And the formula cannot be used. You need to understand this because this will be used in designing PID controllers using root locus. We should ensure that the third pole is 5 times more than the dominant pole, so that second order approximation can be used. Steady state error is also important. We know steady state error is the difference between input, this is input, and output when t approaches infinity. When t go to infinity, then the difference is steady state error. We know that steady state error is normally calculated using final value theorem. SS means steady state, E means error, is limit S to 0, SES. Okay, and where ES equal to R minus C. This formula is known as the final value theorem. It's actually similar to error limit t approaches infinity ES. That is in time domain, but in frequency in Laplace domain, we will use limit s to 0 SES, and that is called final value theorem. And of course, our aim is to have a zero steady state error. Besides steady state error, we also have what we call static error constant. I'm not sure whether this was taught in your section or not, but I mentioned to the student static error constant. We have Kp, Kv, and Ka. Kp is known as position constant. Kv is velocity constant. And A, acceleration constant. They are used to describe steady state error. Okay, sometimes a system is given the value of Kp, the value of position constant, Kv or Ka, in which error is 1/1 plus Kp, or error is 1/Kv, or error 1/Ka. All depending on the input response. Kp is related to step input. Kv related to the ramp input. And Ka related to the parabolic input. Okay, please revise steady state error. They are important. It is used in designing controllers as V1 error equal to 0. So we have to design PID controller so that error becomes 0. Finally, is stability and Rose-Wills criteria. Stability also very important. To be stable, all pole must be on the left half plane of S plane. Okay? If we have 10 poles, all poles must be on the left in order to be stable. If only one be on the right, then the system will be unstable, because that one pole will give exponentially increase. It's not decay, it's increasing. So e to power of 80. E to power of 80 is increasing with time. Then the system will be unstable if only one on the right. Pole on the imaginary axis give a critically stable system. So if we have pole on the imaginary axis, we may have a critically stable system. If no pole on the right, then system will be a critically stable system. If at least one pole lie on the right half plane, the system will be unstable. If only one pole on the right, then it will be unstable. It will increase over time. And one technique to determine the stability is Rose-Lewis criteria. I hope you already familiar with Rose-Lewis criteria. Rose-Lewis criteria consists of table, and also you have to interpret the table, and you can determine the region of the pole, either on the left, on the right, or on the imaginary axis. Therefore, we can make conclusion on the stability of the system. Rose-Lewis cannot determine the exact location of the pole. Rose-Lewis can only determine the three regions where the pole is located. It cannot determine exact location. For a higher order system, we of course cannot, we are not able to calculate the pole manually. We can use a computer, of course, such as MATLAB. We can also use, if we have an advanced calculator, can also help us to find the poles. But in this case, in order to determine stability, Rose-Lewis is sufficient because we can estimate the region where the poles are located. I finished with this part. I will show another slide. Let's move into, in 10 minutes, let's move into chapter 1. I haven't uploaded this slide. I will upload after this, after adding some more things in this slide. Topic 1, the root locus method. Topic 1, discuss root locus. The root locus will later be used to design PID controller. So you need to properly understand the root locus. The root locus is quite abstract. Is deal with drawing, plotting. So please ask if you have problem, if you have question. I admit it will be quite difficult to understand at first because it is an abstract thing. Sorry. Should start with this. Root locus is a powerful method of analysis and design of stability and transient response. Okay, we normally design to obtain a stable system and to obtain a desired transient response. Control engineers usually encounter problem with changing system parameters. What we meant here, let's say I have a system, a block diagram here. I just redraw that one, K1. This is GS, the system. This is a closed loop system with K. The K here is a gain. This is input, output. In many cases, control engineers have problem with changing parameters. This is fixed, GS fixed, but we have K. K here is changing. Maybe at one point K equal to 1, K equal to 3, later K equal to 10. The problem is, what is the best K in order to make sure the system is stable? And what is the best K in order to find or to obtain the desired transfer response? Let's say I want a system to operate at 10% overshoot. What is the best K to get 10% overshoot? Or I want system to operate with settling time 1 second. We need to find K, the best K, to give 1 second settling time. Or some cases, we want both. We want settling time 1 second, we want overshoot 10%. Can we get K that can achieve both criteria? We can see from here, if I take the closed loop transfer function, the formula, remember the formula, GS 1 plus GS, HS. This is to obtain the closed loop transfer function. In this case, this is a unity feedback system. Unity feedback means H equal to 1. Then we can omit this one. Then will be K1, K2, S1 plus S, S plus 10. Sorry. I need a larger space. Closed loop transfer function is K1, K2 over S, S plus 10 over 1 plus K1, K2, S plus S 10. We normally try to get a common denominator. Then if you solve, you get K1, K2, S, S plus 10 plus K1, K2. Or K1, K2, S squared, 10S plus K1, K2. This is the closed loop transfer function. And if I change K1, K2 into K, this one K, this one K, where K equal to K1, K2, then we can see that the denominator here has the value of K. As we discussed before, the denominator is important because it determines the order, the system order, and we can obtain the pole from the denominator. As the value of K appear in the denominator, then K affect the poles. Therefore, K will affect the performance of the system. For certain value of K, we may get a system under that, maybe. Another value of K, maybe system change. maybe at certain K, system will be unstable. It could happen. So K is very important, and our aim later is how can we obtain the best value of K in order to achieve our specification. Let's say this one. Let's take K equal to 0. When K 0, the closed loop transfer function is the denominator become s squared plus 10s plus 0. Therefore, the pole, you calculate pole become s plus 10. Pole equal to 0 minus 10. When K 0. When K equal to 5, for example, the denominator become s squared plus 10s plus 5. Then we can calculate the pole by using, you can solve by using your calculator. You get pole, and this is what you get. When K 0, pole will be minus 10, 0. 0 minus 10. When K 5, you solve this one equal to 0, you get s plus 9.47, s plus 0.53 equal to 0. Then s 0.97, 9.47 minus 0.53. And so on. We can try 0, 5, 10, 15, 20, 25. 25 s squared plus 10s plus 25 is s plus 5, s plus 5. Then we get minus 5, minus 5. We can continue 30, 35, and so on until 50. You can add more also. Then we get imaginary poles. So we can see that the pole move when we change or when we increase the value of K. So pole is very important, but they are now determined by the value of K. If I draw here, based on this, we can see that it's S-plane. When K0 is here, 2 pole, K0. K0, the pole is at minus 10. Here minus 10 and 0. When we change K to minus 5, it go here. Minus 0.53 and minus 9.47, minus 9.47. Here, K, I should change the color. Different K. K now 5. We also increase again until, let's say, 25. When 25, the pole is here. There are 2 poles at the same point. You see 25, minus 5, minus 5. 2 poles here. When K 25. When we increase K, let's say 40. 40 minus 5, J 3.87. So now here, minus 5, J 3.87. This is K when K 40. When K 50 is increasing. Here J 5. Also another one here, minus J5. When K 50. We can see that the pole change with K, with different value of K. When K0 is at one place, K5 it changed to another places. K25 it is on both on the real axis. K40 it become different. K50 it increased. Both are complex poles. So we can see that the pole move. There is a movement of pole when we change the value of K. Okay, we can see that also from here, it moved from here to here, and this one from here to here. And later it go up and down. This movement is called root locus. This movement, if we can draw from here to here, showing the movement of the pole, we can show direction, and this one move to here, from here, and then go up, and go down. This, the movement is known as root locus. Root here refer to the pole. Locus mean loci, mean how it, what is the pattern of the pole, how it look like when we change some value. Okay. So basically, I will stop here. We will continue later. Basically, root locus is showing the movement of poles, movement of closed loop pole. Okay, because we, in the beginning, we get closed loop transfer function. So root locus showing the movement of pole when we change the value of K. We will continue with this in the next class with the definition of root locus for you to understand, for you to have a more clearer understanding on root locus. Any question before we end today?